The last thing I want to show you that Mathematica can really handle very well are some of those more computationally intensive measures that we were looking for in a graph. Things like, what does the line graph look like? What are the betweenness centralities? What's the Cheeger constant? All of those things Mathematica can handle very easily with just a simple command if you know how to use the right syntax. So I'd like to show you just how easy it is to get betweenness centralities of a graph. Remember that a betweenness centrality is a measure of how crucial a particular vertex is in terms of traveling geodesics from one point to another for all possible pairs of points other than that city. So it's hugely computationally intensive, but Mathematica can do it in the blink of an eye. All we have to do is type in betweenness centrality, and the argument that that function takes in is a graph, and we'd like to compute the betweenness centralities of the graph ADG. You hit enter, and there you go. The betweenness centrality of each vertex is listed here. Now, the most important vertex will be the one with the highest number, but it's very difficult to know what the highest number will be without just walking through each element of the list. So we have a 22 here, and that seems pretty good, then a 26, and then a 50. You get a little excited, but you go further down the list and you see 121, 130, and then all the way on down to this 111 right here. So those seem to be the ones that are absolutely the largest, and we'd be interested in figuring out what cities correspond to those high betweenness centralities, because those seem like important cities to base your strategy off of in the game Ticket to Ride. So to make this a little bit more helpful, what might be a better format is to ask Mathematica to create a table of two things. First, let's have it print out city names at position I, and I will be an iterator. And let's label this list for ease of access. So we want in the first position the name of the city at position I, and then the next thing we want listed is the betweenness centrality at position I. And our iterator I should start at 1 and go the length of that list BC. So going through this list, it seems as though, from a vertex standpoint, Denver, Helena, and Pittsburgh are the most important cities. Now, another thing that would be difficult with such a large graph would be to create the line graph of our Ticket to Ride game board. Part of the reason that I want to do this is as follows. It is true that these cities that we've identified, Denver, Helena, Pittsburgh, seem to be important cities, but the game of Ticket to Ride is more about claiming routes with your trains. So I'm not as interested in what cities seem important as what routes seem important. Which roads on the game board do I really want to claim, because they're fundamentally essential for the transit of many different paths. And those are the things that I'm particularly interested in. So if I could compute the betweenness centralities of the line graph of my original game board, that would be much more valuable information for my Ticket to Ride strategy. And Mathematica can create the line graph for a given graph very easily. All we need is the command line graph of our graph. We hit Shift Enter, and voila, there it is, drawn as beautifully as we can get it. Now, that's horrifically not useful to me because I don't know what any of those vertices are, and that's a much more difficult question than it was the first time around. The first time around, I had a key that had my city names and I knew what order I had listed them in, 1, 2, 3, 4, whatever, but I have no idea what Mathematica just did internally to create the ordering scheme on all of these vertices. And so as much as that's a useful graph in theory, it's not going to tell me what I need to know unless I can force it to impose my labeling scheme of city names on those vertices. So there is actually a way to do this within Mathematica. This is a little bit fancy just so we can get a meaningful answer for what we're doing. But what Mathematica does is when it has a graph like ADG there's a function you can apply to that graph called edge list, which gives you a list of all the edges. So here I've named that list edges so I can refer to it later, and let me show you what that looks like. So if I came back up here to this graph and told Mathematica that I wanted to see vertex labels, it puts vertex labels on it, a lot of vertex labels, and they correspond to the positions in this list. So it is possible to recover that information if I wanted to. Where I see the first vertex, right over here, that's representing the edge between vertex 1 and vertex 2 in my ADG graph. So it is going to be possible for us to go back and forth to our actual city names. But if we're willing to put in a little more time with Mathematica, Mathematica can change these vertex labels to be arrows between two different cities with the right kind of code. So I don't want to take time in the video to step through the code. I will be posting the Mathematica document online, and this was not something that I knew how to do automatically before I started working on this program. So this was all stuff that I came up with from looking at the help manual and looking at the format of the different commands in Mathematica. So it looks like what I've done right here. Let's evaluate this cell and then see what's going on. I made a list that now has, just like I had the list of city names up top, and then I was able to tell Mathematica, replace vertex I with city names at I, I've created something called ticket to ride edges that seems to be a large list of what I want the labels to be on this graph for the vertices. And then in this command down here, I'm going to tell it to go ahead and apply those labels to the graph. And there you go. Now I've got them here. All that remains is I need to take a look at the betweenness centralities of this graph and find the largest one. So let's take a look at betweenness centralities of this graph. And let's use that shortcut in Mathematica, %47, 47th output. And it gives me a list of those betweenness centralities. Now this is a longer list, so going through it and figuring out which numbers are the largest might be a little more time consuming by hand. So what I can do is ask Mathematica to sort this list for me. But before I sort, let's do the thing we had done with the previous graph where I asked Mathematica to print out pairs for me. Instead of printing out just the betweenness centralities, why don't we print out the corresponding edge in our original graph and then the betweenness centrality right next to it. So in other words, we'd like it to display ticket to ride edges at position I along with the, let's label this LGBC or line graph betweenness centralities so we can access it a little bit easier. Position I. So this code will display the edge in the original graph and the betweenness centrality right here. And we want to do that for as many things as we have in that list. Now let's have it sort this list according to the second component. Now unfortunately, when we just apply sort to the output of our previous input, it sorts things alphabetically, which is not really what we want. We want them to sort things numerically. So let's see if we can fix that by just changing the order of the ordered pairs right here. So instead of putting the edge first, let's put the betweenness centrality first and the edge second. And then let's reinitialize everything and see if that sorts in the order that we're looking for. That output is now the 56th output, and it has exactly the effect that we want it to. When we jump to the end, we see that Denver to Helena has the highest betweenness centrality, followed by Helena to Duluth, and Denver to Oklahoma City. So right in that middle towards the west coast, we're getting these real high betweenness centralities, and those seem like the routes most worth claiming.